Hello, good evening. I'm sorry for the delay. Today we're going to discuss about generative adversarial networks. This is a really interesting topic. I'll try to present it um, in the remaining time, but if I'll not manage, I'll try to extend the time a little bit, maybe half an hour, so that we can give it enough time. Just let me know in the meantime if you can hear me well, and if you can see my screen sharing, then I will start. The lecture. So please, if somebody can write in the chat that you're ready to start. Not sure, so I'm streaming from a different location, so perhaps the delay could be larger. I'm not sure about this, but we'll see. Okay, I hope I don't have a problem with the connection, and it's just a delay problem, so I hope to see some okay in the live chat so that I know I can start and you can hear me well. I had the sound off, but I'm not sure if this was a problem, so it's not the sound. Okay, the important thing is that you can hear me. Okay, thank you. So yeah, I also posted the link on Facebook, so as usual, but only later this time. Okay, so I apologize one more time. Okay, let's get into it. So today we're going to present generative adversarial networks. We'll discuss about various developments on top of these networks that were done along the years, and also we will discuss about CycleGAN, which is a bit different than the original generative network, and it has slightly different applications. I think the results are a bit more realistic. Of course, it doesn't have such broad applications as the standard GAN, but the idea is that this topic is very interesting, at least in the research community. So the paper that introduced this model in 2014, it was proposed by Ian Goodfellow, and now it started to grow exponentially as a topic in computer vision and in related fields, and now it's really a mature subdomain of computer vision. So, but it only started in 2014, so this is a very recent topic. So the main idea with generative adversarial networks is to, as the name implies, we have some generative network here. So we have a generator that we want to use in order to generate or to synthesize images. And how we approach this task, mainly we have this network, and we also have a discriminator. So the generator and the discriminator are adversaries. So this is why the model is called generative adversarial network. So the generator tries to generate realistic images, while the discriminator tries to act as an adversary and say if these generated images are real or fake. So the discriminator also sees real images and fake images and is trained to discriminate between these. And the generator is trained to generate images that are as realistic as possible. So they are acting as adversaries. So the generator is trying to fool the discriminator, and the discriminator tries to fool the generator. Okay, so commonly the architecture of the generator or the discriminator can be the same, but it also can be, the discriminator can also be a more lightweight architecture, because it was observed in practice that the task for the discriminator, so the discriminator has to decide if the image is real or not, is easier than the task of the generator. So if we really put here a model with very high capacity, then the generator will have no chance. So in many cases the discriminator is a simple architecture compared to the generator, while in some other cases we can use the same architecture in a mirror. So here we have some components that are used in the generator, like transpose convolution and batch normalization. These are seem to be quite a big deal for the generator, so these are required in order to generate useful images. So the main idea with this architecture is that they are kind of an alternative approach to probabilistic generative models. So in these probabilistic models, the goal is to build a model that generates synthetic observations, and the goal is to make these synthetic observations as realistic as possible. So this translates to a density estimation task. So we want the probability of the real data of our observations to be equal to the probability of the synthesized examples. So using probabilistic models, we're trying to model the probability of the observations, and then we can generate new examples from this probability. So this is the main idea, and this can be done in various ways, like for example applying maximum likelihood estimation. So we just estimate these parameters of our model such that we maximize the expected value for the data that is observed times the logarithm of the probability of the model to output the example x given the parameters theta. Okay, and this can be done, for example, using an explicit and analytical approach. So this is the case of Gaussian models. So we approximate this probability with a mixture of Gaussians, and then we can sample new samples from this Gaussian distribution. Another approach is to use Boltzmann machines, which can estimate the probability by running MCMC. And third, there is this new approach based on generative adversarial networks, which is implicit. So what this means is that we do not model the density function directly. So instead we just learn how to estimate from this density of probability without actually being able to get our hands on the actual function. So GANs are just a generative model that learns this probability implicitly in the model. So we do not know the actual probability of the model. We're just trying to approximate the probability observed in the real data. Okay, so with adversarial networks, we have a generative model that outputs a generated image, and then we have also a discriminated model that takes this image as input and decides if it's real or fake. And of course, the task should not be trivial for the discriminator. So along with this generated image, we also have to include real images. So the discriminator will really have to decide. So otherwise, if we just use the generated images like this, it might learn just to output, let's say, the label 0 associated to generated images. So this would be trivial. But if we also include real images for the discriminative model, then at prediction time the task will not be trivial. So we'd really have to decide if the image is real or not. Okay, and one problem with the generative model is we do not want this model to generate the same sample every time we run the model. We want to generate various samples. So in generative adversarial networks, this is actually done by starting from an input, which is actually a noise vector. So it's a random noise vector that is generated, and from this random noise vector we get a specific sample. So the model actually has deterministic output for a given noise vector. So the way we make it non-deterministic is by regenerating the noise vector randomly each time we want to get a new example. Okay, so the generator is a model that is differentiable, so it can compute the output x given the input z and the parameters theta, and this vector z can have a very high dimensionality. Okay, so about the discriminative model, this acts as an adversary for the generator, so it is also a neural network. So the discriminator outputs two binary values, or actually class probabilities, between 0 and 1. So it should output 1 if the image is real and 0 if the image is fake. So this is what we expect from the discriminative model, and this is also important to remember these outputs when we'll discuss about the loss function in a few moments. Okay, so the training procedure is we train these models jointly. So, but the training can be actually in one step. We can try to train the models alternatively. So we have these models that try to act as adversaries. So as we improve one model, the other will have a more challenging task. So if the generator generates better images, then the discriminator will also have to learn to really look for finer details into the generated images in order to figure out that these are not realistic. And in the same time as the discriminator gets better, then also G has a more challenging task in generating more realistic images in order to be able to be an adversary to the discriminator. So in the end, so we train these both the generator and the discriminator, but the ultimate goal is not to use the discriminator, but to use the generator. So we want to train a generative model. So our role is actually to make sure that the generator is really good. We do not care so much about the discriminator. It is just used to obtain a good generator. Okay, so for the discriminator, we have the binary cross entropy as loss function. So we have this loss that is defined as so the discriminator should output the value 1 if the example comes from the real world. So if this doesn't happen, then the loss here will be higher, and this is the loss for synthetic images. So in this case, the discriminator should output the score 0. So if the score is higher, then we'll also have here a positive loss. So so this is the loss for the discriminator, and the loss for the generator is actually opposite. So or it should be the opposite loss. So one tries to make sure that it can discriminate between real and fake samples, and the other wants to generate fake samples that are as realistic as possible. But actually, for the generator, it cannot influence this part. So the generator only plays a role in this part of the loss function. So actually, the loss for the generator is only this side of the of this loss function. So the LG will be minus LD, but actually we use this part of LD for the discriminator. So because this the generator does not influence this part when we do gradient descent on top of it. Okay, so this training procedure using by maximizing this loss and also minimizing in the same time is called the min-max procedure. So this is the procedure that was introduced with this model in order to be able to train it. And the training is done also with stochastic gradient descent as for other types of neural networks. And in the mini batches we use some generated samples and also some real-world samples. So the mini batch has to contain half of the samples have to be generated and the other half should be from the real world. Okay, so training the discriminator is straightforward. It's not such a complicated task. It's just as any other classification model. Yeah, backpropagation is pretty standard, but for the generator, actually the gradients are backpropagated first through D. So the loss depends on D and then also depends on G. So we first pass the gradients through D, and then the gradients can also reach the generator. So there are two ways to think about this. So first we can freeze the weights of the discriminator and then propagate the loss of the generator through D. So the other approach is we compute the loss of the discriminator with respect to the input X, and then we propagate the gradients with the negative sign to the generator. Okay, so as I said, D can be trained without altering G, and also G can also be trained without altering D. So when we train the generator, we freeze the discriminator, and then when we train the discriminator, we freeze the generator. So these are done alternatively until we reach convergence. And then it is also possible, so it is not necessarily that we train one iteration for the generator and one iteration for the discriminator. It can also be that in some cases, for example, we want to do more iterations for the discriminator in order to make sure that it stays ahead. Or we can also do the other thing for G. We can try to iterate several times to G while we iterate only once to D. So these are possible training strategies and people have used it in practice. So the discriminator learns when it is able to estimate the probability of real examples while excluding the synthesized examples. So what the generator is trying to do in the same thing is to map the noise vector Z to the sample X, to the samples X that model this distribution of the real data. And actually G has more of a reinforcement learning task. So because it knows when it does good, so it knows when it can fool D, but it does not know when it not its output is not that good. So if the generator is generating wrong outputs from the beginning, it will be hard for it to find the right path to convergence. So first we might want to use more iterations for the generator in order to catch up with the discriminator. Okay, so yeah, the problem is we can describe the optimum via a single loss. So there are two losses, one for the generator and one for the discriminator, and the goal is to reach this equilibrium between the generator and the discriminator. So we note that once again, I think I mentioned before, but maybe with other words, that the discriminator is rarely fooled in practice. So, but even in this case, G can still learn because the gradient of D also provides some information on how to adapt the generator. So it can catch up, but we have to allow it to make more iterations. Okay, so in the original paper of Goodfellow, they also studied different different losses for the generator, and in practice they all seem to produce sharp examples. So the model seems to be able to generate sharp examples in sharp, I mean, without blur artifacts, in irrespective of the loss function, but people nevertheless studied other loss functions and tried to improve better models by changing the loss. Okay, and okay, so this is a brief detour to deconvolutional neural networks. As I said, it is important in the generator to have the convolutional layers and batch normalization. So these are important to generate images. So the convolutional GANs were introduced in 2015, and they seem to be able to produce more realistic images. So the main idea was to use the transpose convolution, which essentially takes the input and adds some padding between the input in order to generate maps of higher dimension. So I think I explained this also in the last lecture, so I'm not going to discuss too much. Also in their paper, in the convolutional GANs, they use leaky ReLU for the discriminator. They observed that this is an important change for the model to learn better. And they also added batch normalization. So in batch normalization, given a set of samples from a mini batch, we compute the average for the mini batch. So the average for each element, each feature in the samples. We also compute the variance, and then we apply the normalization. So we subtract the mean and we divide by the variance, and then we allow the model to rescale and shift the average and the standard deviation to a different interval. So we also have these learnable parameters, which represent the new mean and the new variance of the data. So the good thing about using batch normalization is when we use, for example, a sigmoid, many of the data that, if it's not normalized, it will be outside the region that has gradients with high magnitude. So for example, for these data points, the gradients are close to 0, so the model will not update. And for the normalized data, most of the data lies in this region, so now the model will update better. So batch normalization is important. Yeah, so this is a model that is configured, so it has batch normalization, ReLU, the convolution. Here at the end it has either sigmoid or hyperbolic tangent as loss function, and the discriminator is based on convolution, batch normalization, so this is also required for the discriminator, and using leaky ReLU for the activation functions. So they also applied, so this model is the standard model applied on NIST. So here we want to generate images of 28 by 28 pixels that are grayscale. So the model, a simple model, could have like 3 layers. So this is what they tried out on MNIST, and the discriminator has the same components mirrored on the other side. Okay, and so this is the generator and this is the discriminator, and one way in order to improve the generative results. So far, GANs, so as I presented them so far, GANs are considered, so the standard approach is considered an unsupervised model, because you don't need a label for your data samples. You just need a set of realistic images without any annotations, and you can use these images in order to generate or to synthesize images that are realistic, but without having any labels for the data. So the model is unsupervised because humans do not provide labels for the data. But there is also this idea that appeared after the initial paper of GAN, which is called conditional GAN. So the idea is to add some one-hot label with the classes. So when we generate a noise vector, we also associate a one-hot label for it, which corresponds to the classes in your data set. So in this case, these are the classes for MNIST. So then you will produce images for the corresponding class. So here you produce actually a 3D tensor, and you will generate the image on the position of the corresponding class. So if you want to generate a 0, we will generate a 0 here, and the rest should be filled with elements with 0. If you want to generate a 9, all the maps besides the last one should be filled with 0, and the last one should contain a 9. So we generate the example on the location corresponding to the class that is provided here, and this is a conditional GAN. And in the original paper, they only added this class to the generator, and recently they also observed that using this idea in the discriminator is also useful. So the discriminator not only discriminates between fake or real images, actually discriminates between fake and the different classes of real images. So it has to say that this is a fake image, or this is an image from class 1, and so on. Okay, so labels can improve the generated samples. So they observed that using this idea improves the quality of the generated samples visually, but it also provides the means to generate samples for specific classes. So if we want to generate an image for, let's say, with a horse, then we just make sure that the one-hot encoding that is given as input to the generator has 1 corresponding on the horse class position, and then it will generate a horse. So here we have a comparison of generated images with the original GAN, with some improvement on top of GAN, which is called LabGAN. So this is contains multi-resolution the convolutional pyramid. So it is a model that can produce better results. And then they also have results with different classes. So here they actually show results for the class deer, for class dog, for class frog, and so on. So for different classes they now generate specific images, and you can still see that within each class you get variability inside the class. Okay, so they also seed the generator with low resolution images plus class. So this was another extra idea. So not only add the class, but also add some low resolution image that can be provided as input. So here they provide, for example, the label bedroom and this low resolution input, and then you can see what the network can generate from this input. So this low resolution image has kind of the same colors and background with this generated image, but this is actually the image generated by the gun. So this is also an idea that was explored. Okay, so in order to train a gun, we have this pseudocode implementation. So we have some input that is the vector z and an image, and optionally, if it is a conditional gun, we can also add class labels. The network is actually formed of the two models, the generator and the discriminators. On the discriminator, we also have a loss, two losses, one for the generator and one for the discriminator. And for the optimizer, of course, we want to optimize both models jointly. So typically this is done using stochastic gradient descent. So for a number of epochs and for a number of mini batches, we first update the discriminator and then we update the generator. And here, as I said before, optionally you can try to update one of the models several times while you update the other model only once. Okay, so there are also schemes to ensure that samples are diverse. So one idea proposed by Salimans is to look into the samples that are included in a mini batch and just make sure that these samples that are generated are not so close to each other. So they just use a nearest neighbor in the latent space, in the latent representation. So this is the space of the noise vector z. So they just make sure that they generate vectors that are far away from each other, so that the samples from the mini batch are diverse. Okay, this has also been applied on ImageNet. So yeah, if you look closely, so one of these batches is realistic and the other is generated. So if you look closely, you will figure out that the left side are real images and the right side is with generated images. And if you look more closely at the generated images, so these are cherry-picked results from these preliminary works until 2017. And you can see you get some objects like, I don't know, things that look like rabbits or like dogs and so on. But if you look up closely, you will figure out that these are not, cannot be real. So what problems are encountered with the generative network? There are problems with counting. So for example, this is kind of a creepy example with in which the model generates more than 2 eyes for different classes of objects, and so it just if it fools the discriminator, then for the generator this is a good image to generate. So yeah, there is this problem with counting, also a problem with perspective. So the same object is kind of viewed in the same time from different perspectives. So you can see, for example, this cat here that is viewed really from, we also have a dog, a head here, then I don't know, this looks like a back in the same time. So these perspectives are not really realistic, and also problems with the global structures of the object. So I don't know, things like missing legs or bodies that are distorted and so on. Okay, so yeah, the images are generated, but sometimes the object do not look so realistic. Anyway, so one approach where we can generate more realistic images is when we provide the images as input to the generator. So one example is the idea to predict future frames in video. So you have some sequence of video and try to predict the future. So if you try to use, for example, so this task was not really approached before, so this means that GANs also enabled new applications. So here we see an example with a head from a future frame, and how the prediction, if you just average the last results, you get a blurry prediction. So this is the result using the mean squared error to produce the future frame. And if you use adversarial training, you get a sharper object that is closer to the input. And the model was also applied to single image super resolution. So you have an input image that you want to increase the super resolution. So this is the result. So this is the original image, the one that you target. The actual image is twice as small, so the actual input is smaller. So what you see in the actual input is perhaps something like this, but of course reduced to a smaller size, so it's less blurry. So when you try to resize the image with bicubic interpolation, you get this result, and this is some method from the related art that is not generative net, and this is also result with their this paper called Super Resolution GAN. So yeah, they show in several examples that they can really minimize the noise signal to noise ratio with respect to these other models. Another interesting application is to generate fashion items. This has application in the context of recommender systems, and these authors collected images, and they also have the the preference of the images. So they also know this space of what images are preferred and what images are less preferred. So yeah, then they can use they can use again to recommend fashion items. So they can actually predict these directly from images. They can predict what images are interesting. Okay, so usually this is done from predefined sets of fashion items. So the twist here with GANs is we generate images from scratch. We do not take, or we do not select an image from a predefined set. Okay, so they employ the class conditional generator and discriminator. So they use class conditional through both generator and discriminator, and they make sure that they optimize the GAN such that it obtains a latent representation that obtains the high recommendation score. So yeah, these are some fashion items that they generate. So they have a prototype example, and from these they generate an example that is can have a higher recommendation score. So you can see that actually the model is trying to make the colors brighter, or to transform, I don't know, black pants into red pants, I don't know, white shirt into a blue and bright shirt, and so on. And they also analyzed how the generated models compare to the top real examples from the dataset that have that have a high recommendation score, and they observed that these are fairly similar. Although I think that the network perhaps generates more colorful examples. So yeah, if you look actually closely to these examples, you will see that I don't know, at least for myself, I would really opt from these choices here. I'll probably like one of these instead one of these. So usually probably just because if they're more colorful, or I'm not sure, but yeah, they seem more diverse, more appealing. Okay, so yeah, this ends the discussion with GAN. So Okay, so far there aren't any questions, so this is good. So yeah, the second part of the presentation is dedicated to cycle GANs. So yeah, this starts with perhaps the topic of image-to-image translation. So before cycle GANs were introduced, I think the state-of-the-art model was called Pix-to-Pix network. So this was a network that was able to translate images that are paired. So for example, you have this input image with segments from a street scene, and you can produce this output image, or you take an input black and white image and you produce a color image, and so on. So you can also, for example, take a terrestrial map and produce the satellite version, and vice versa. You take the satellite version of the map and you produce the terrestrial version. And you can also transform day to night images and sketches to real objects, and so on. So this has an interesting way to do things. So given these image collections, the algorithms learn to translate an image from one collection to the other. So the main difference from the previous work is that cycle GANs do not need pairs of images. They just need these two image collections. So for example, in using Pix-to-Pix and other similar works, based on networks that do image translation, you would need pairs of images. So you need the sketch and the corresponding image with the object in order to train the model. So the model will take this as input and will try to reproduce this output. So this is how the model works. But in some cases, it is expensive to collect these pairs. So in this case, you actually need to take a car on the street and to drive it around and collect these street scenes, and then to label all the objects, and in order to get the segments so that you can generate images for this case. And in some cases, it is very difficult and expensive to obtain the data set. But in some cases it is not possible. So for example, if you want to translate images of horses to images with zebras, so this intuitively for humans is not such a complicated task, right? You just have to draw some stripes on the horse and everything else stays the same. And actually you cannot have pair of images in this case. So yeah, you cannot take in the exact same location a photo with a horse and a photo with a zebra in order to be able to translate. So it's nearly impossible. Okay, so the idea is, if we just take these collections of images with horses and the collection of images with zebras, we just want to learn to do this transfer between horses and zebras. And this is done with these cycle GANs. So the main idea is, for example, if we have here a generator that takes as input an image, we also use this real image for the discriminator. So the generator generates an image. So here we do not have input-output pairs, so it can take this image and generate this image, and it can fool the discriminator, so it might look real. But it's not necessarily that the generator will generate the corresponding image. So it can also generate a different image, and the discriminator will also say that this is real. So the problem is that GANs do not force the output to correspond to the input. Okay, so this is implicitly learned, and what the model can do actually is, for different, in this case, taking as input different images with horses, it will map all the images to one realistic photo with zebras, and then it will generate only one sample. So this is known commonly in generative networks as mode collapse, when the model collapses to generating a single input or a few single outputs. Okay, so the solution here is to use cycle consistency. So what this means is we have this data from the domain X. We have a generator that maps it to the domain Y, and we also translate it back to the original space. And when we do this, so let me just explain this in more detail. So actually in cycle consistent GANs we train two generators and two discriminators in the same time. So here we have an example X from the original domain X, so an image with horses, which translated to the domain Y. So here we obtain an image with some zebras, and we have the discriminator that tells us if the image is realistic or not. But what we also do, we also have another generator F. So this generator translates this generated image back to the original domain. And well, through the translation process, it might not go to the same output, especially if these are not enforced in any way. As I said before, the generator does not enforce the same corresponding output to the input. So in order to enforce this to correspond to the input image, we add this loss. So this image has to be close to the starting point, to the image that was used initially from X. So this component is added to the loss function, and this is called the cycle consistency loss. So when you do a complete cycle from X to Y and back to X, then you need to make sure that you get to the same point, or as close as possible to the initial point. So then if we include this cycle consistency loss, assume that we have this model that was doing mode collapse previously. So what will happen with mode collapse is that then we go, when we take this image and we generate and we translate it back to the original domain, well, from this image it will map it to probably a fixed input, perhaps one of these. With mode collapse, it will generate one image. So what we do is, if we add cycle consistency, of course for this image we will have a small cycle loss here, so this image is close to the original one. But for the other examples, here we will have a large cycle consistency loss. So we start from this image, we generate this one, and then generate this one, so we will have a large distance in the space X between these examples. So therefore, in order to minimize the cycle consistency loss, we will force the network to generate here an example that is closer to this one. So it will naturally go out of this mode collapse. Okay, so actually here when we want to translate from X, from the domain X to the domain Y, then we train two generators and two discriminators. And when we want to do the other way around, so sorry, actually we train two generators and one discriminator. And if we want to do the translation from the other domain back, then we train a different GAN. So actually here the results of this generator F are not as good as this generator G. So essentially we train this model with the generator G and the generator F and the discriminator dy in order to obtain this generator to translate images from X to Y. If we want to do the reverse translation, we train the model independently for this translation. So and this is done in the same way as here. So the idea of cycle consistency is borrowed from the vision domain. So this idea was previously used in vision to find, for example, to find the detection of tracking failures. So you take some key points and you see if they are the same in different frames. Then you have some consistency between them, then it's okay. Otherwise you have a problem with your track. So this is an inconsistent track, and this has been applied in different domains. So also in finding collection correspondences between images. So you can actually train a model, for example, by taking this key point as input to predict the corresponding key point for this image and for this image and so on. And you can do this without any supervision. So if you do here a full cycle, you make sure that when you reach back to the original image, you want to reach the same point. So you don't need to add any labeling, and you can learn useful features using this collection correspondences between key points. So here you learn discriminative key points for objects, and so on. This is a similar idea that learns the same idea of key points. Okay, so now we're moving to the results. So these are the results from the CycleGAN paper that was introduced at the ICCV 2017. So CycleGAN is a more recent model. And they compare with other types of GANs, and they really show that they are producing more realistic images. So mechanical Turkers were used to label images as real and not real, and they observed that their CycleGAN surpasses the other GANs by a significant margin, but it's still so it has like perhaps 1/4 of the images look real, but it's still a long way to go until they look completely realistic. Still, the results are quite interesting. So here we have some results with a horse that is transformed into a zebra. So you can see that the horse is translated, but the GAN also introduces some these zebra patterns in the branches here. So it learns to the main thing, but it also adds some artifacts to the image. And this is translation from orange to apples. Once again, another example from orange to apples, and you can also see these artifacts that are added. And actually it's nice that it also kind of changes the leaves. So these bright green are changed to these less bright green that are more seen in apple trees. Yeah, the model was also used for style transfer, so you can take a realistic photo, and if you translate the generator, I don't know, with paintings of Monet, then it can translate these realistic photos into images that look like paintings of Monet, and you can do this for different painters. Yeah, this is an example with some real images that are translated to the style of Monet, Van Gogh, Cézanne, and so on. They also did the translation of paintings of Monet to real images, and you can see here some artifacts, but this really looks more realistic than the painting. So this is quite interesting to see how the landscape that was painted by Monet could actually look like. And this is another example of painting that is translated to a real photo, and you can really see that the sky looks more realistic, the water, the reflections in the water, and so on. And here also the reflections of the water are recovered, but it's still the boat looks more like a painting than a realistic boat. This was also applied to landscape to transform summer into winter and winter into summer and so on. Okay, so the main idea behind CycleGANs is that the style is more easy to transfer than content. So actually in images we have this separation of style and content of let's say objects that appear in the image and the style that they are produced. So this separation is kind of represented here with letters. So if you look on this axis, you have letter A in different styles, and here we have the same style but different content. So the main idea is that CycleGAN works because translating the style is easier than translating the objects. So, since these are somehow decoupled, you can use this adversarial loss just to change the style without changing the content. But this is done in the cycle consistency by actually making sure that you preserve the content through the cycle consistent loss. So this is an explanation why the cycle consistency loss works well in transferring the style and not changing the content of the input. So the assumption is that content is easy to keep and the style is easy to change. So we want to keep the content of the image but just change the style. Okay, so this was done in literature with neural style transfer. So there are these GANs. You have some input image, some image of a specific style, and it can transform this input image to an image with the style from this image here. So the same happens here. You have this image that is repainted in this style, and this image that is in repainted in according to this painting. So the idea was you can get an input image and different styles and obtain the same painting, but actually if you CycleGAN is able to really capture the style on Van Gogh without exaggerating. So here we have some exaggerations that are not really so realistic. Here the same. If we go from horse to zebra, so we have this input and style use this image of a zebra as style. We get this this image which really doesn't transform the horses into zebras. Here we have a different image as style, and here once again this neural style transfer fails, and the result with CycleGAN is actually a bit better. Okay, so for CycleGAN you have different implementations. I think that these are the official implementations in PyTorch, but there are also other implementations, so in TensorFlow, Keras, and so on. So there are many applications of CycleGANs that you can try. So it was used, for example, to translate. Sorry, I got a notification. You can use it to translate video games into real images. So this can be used, for example, for video games. You can generate these scenes and also generate object annotations that is pretty cheap. So this can be obtained through while you generate the scene. And then if you want to train an object detector for real images, you can use CycleGAN to translate these images into a realistic image. Okay, and these are examples that are generated real images that are generated into video game images. So it is also possible to generate video game scenes from realistic data. Yeah, this is the application that I showed before from that I mentioned. So you can get this synthetic data from video games. You automatically have segmentations because you know the objects in the scene, and then you can use this data to train a model to detect objects on real images. And yeah, if you just train on these video game scenes, you obtain a score that is very far from a model that is actually trained on realistic data. But if you use CycleGAN, you can really get some significant improvements here, and also this is a per pixel accuracy. So this is still research going in this area. We our group also studied this task, and probably I'm going to show a few slides in some future lecture. But still, the idea of using CycleGAN in this task is really interesting. And if you do not have this data annotated, you can try to use generated data plus translation with CycleGAN to obtain some labeled images. Okay, so we also have applications in object editing. So you get some shape of an object, you get the input, and you can transform it into a cat. So you, in addition to doing translation, you also add this mask into the equation. So you make sure that the network acts only on the object that is in the defined mask. You can also use it to generate images with different attributes. Okay, you can also use CycleGAN to enhance images. So you have these images from street scene, and after you apply a CycleGAN to enhance the colors and the brightness and so on, you can obtain a much better image. You can also apply to image dehazing. So there is this task where you have images with haze and you want to remove it. So you can apply CycleGAN to transform, to translate. So you just need a bunch of images with hazing and another images without, and you can learn to translate and to dehaze images. It has also been used for unsupervised motion retargeting. So you have an input motion on an object that is moving in a certain way, and you want to make other characters move or to repeat these motions. And this has been also CycleGAN has also been used in this area. Okay, so this is a video with that tells you more about this application. So I think I'm going to skip the video now and let you see it by yourself. And of course, there are also applications beyond computer vision. So there are applications in medical imaging, voice conversion, in cryptography, and so on. So for example, in medical images, it was used to generate CT scans from magnetic resonance images. So these are two different devices that can give you these scans. One is based on X-rays and the other on magnetic resonance, and you can actually use CycleGAN to get the X-ray images from the MRI. Okay, so this is just some details about the model. You can also look at the, so yeah, this is looking at the reconstructed images of the CycleGAN, and yeah, this is the input, output, and the reconstruction. So you can see that the reconstructions are quite close to the original images, but they also have some additional artifacts. Okay, and there are also some failure cases. So CycleGAN produces more realistic images than standard GANs when it comes to image translation, but it also has some failure cases. So in this case, for example, it transforms also the human into a zebra. And yeah, this is an example with an apple that is transformed into an orange, and here it loses the structure of the orange, so it looks like maybe an opened orange, but the structure inside is not realistic. So CycleGANs have also been used for multimodality, so you can obtain multimodal images. You can also control the style of images, and you can also apply it on more than 2 domains. So in multimodality, you can take an image and obtain different modes of the same image. So here it translates into genders, into man to woman, but it really can control the modality, like you can translate it into a red-headed woman, with red hair, with black hair, blonde, and so on. So yeah, this was done in this paper called Augmented CycleGAN. Yeah, and the main idea in this paper is that along with translating from images, paired images from A to B, they also add, along with the images, they also add these noise vectors that can use to control the modality. So yeah, using some input image and some noise vector corresponding to a certain modality, they generate this data sample. Then from this data sample, that can recover the modality, and they want to make sure that this modality is close to the original one. They also do it from A, and from this B they can also estimate the modality for A, and then they use this to generate the model A back to the original domain. So then they can compare, they use cycle consistency with respect to the input images and also with respect to these noise vectors. Okay, and these are some results from their paper. As I said, you can also apply this for style control. So this is more close to the neural style transfer architectures, but only using CycleGAN instead. So if you add the paired CycleGAN in the context, then you can obtain these images. So this is a source image, and you can, for example, this was applied for applying and removing makeup from images. So you have this image, and you see that it applies makeup in different styles according to these reference images. And this is trained, once again, you have the reference and the source. So you apply a generator to translate the reference into an image without makeup, and the source into an image with makeup. So you have 2 generators and 2 discriminators here. Then you do the translation back to the original domain. So you use here the generator G to translate this image to this image, and the generator F to translate this image to the original one, and then you have this cycle consistency between the references and between the sources. So this can be used to control the styles. So here we have the source image, the reference image, and the image with the applied makeup. And as I said, you can also apply this architecture to more than 2 domains, but there is this paper that instead of just using CycleGANs between every pair of possible domains, you can use this approach, which is called StarGAN. So in StarGAN, you learn to map each domain to a latent domain using a single generator. So this is a more efficient architecture, and it also seems to obtain improved results. So here you can control, for example, So you take different domains like people with black hair, people with blonde hair, gender, and so on. And then from one input image, you can translate to different domains. So if you use the standard approach with CycleGAN and you train all the generators between pairs of domains, you get these results. But if you train StarGAN, you can really get an improvement. So learning to transfer from all these domains to a latent domain is really useful. Okay, and we also have these contribution that is going in the same direction. So instead of training pairs of models, you train a single model to generate between all the domains. So this is called ComboGAN. Yeah, so in their model they have I don't know, generators, and from one domain image they have here encoders and decoders. So the generator is formed of encoders and both encoders of decoders. So in order to transfer the style from one domain to the other, you learn all these encoders and decoders for each domain. So you have n generators. So you do not have so if you want to train all the possible pairs, you will have n times m minus 1 divided by 2. But here you just train these models independently, but you make the encoders use the same latent space. So then when you try to generate an image, you apply the encoder from the respective domain, and then if you want to generate with a certain style, you apply the decoder from a different domain. So yeah, this was the idea used in ComboGAN, which seems to be better than StarGAN. So this is also a nice extension. Yeah, and there are also results in transforming people into anime art and so on, and transforming into, this is translation between cats and dogs. Yeah, and this was the last slide, so I tried to compress the talk in one less than 1 hour and a half. So I think we can stay maybe 5 minutes for questions before I will move on. Okay, so we have one question. So please, even while I answer this question, if you have other questions, just let me know. I have one update. Just remember to tell you about the Kaggle competitions. So I will probably launch them by the end of this weekend, or at least one of them will be launched by the end of this weekend. So stay tuned. I will pass the sign up link to the lab assistant. So I will not publish it on the website. So just in order to make sure that nobody else enters the competition. Yeah, so they are not already launched. Otherwise you would have known about them. Okay, so now going back to the question from Mihai Matei. So on yeah, so the deadline will probably be by the end of the year, so you will have enough time to work on the project. Okay, going back to this question. So regarding cycle consistency loss, the generator does not see the real data on the input, just a vector space or some noise. So what kind of data? No, the input is an image. No, it's not a noise vector. The input is an image. I think I thought I made this clear. So in cycle consistency GANs, you do not use noise vectors as input. You use images. Okay, so yeah, I see no other questions here regarding the slides, so thank you for your participation, and once again sorry for the delay. Okay, and see you next week. So probably next week, I mean not probably, like most definitely you will have the Kaggle competitions. So next time we will also discuss a bit perhaps about the Kaggle competitions. Okay, so once again thank you for your participation, and see you